Okay, this is the second hour of Physics 1C for whatever today is, the 18th of February. And we're going to start off by doing this problem that's right here on the board. And I'm going to have you all do this problem, actually. I'll set it up a little bit. And then I'm going to have you try to calculate it. It'll give you about 5 minutes. And then we'll come back and talk about it. So what we have here is, I don't know how well you can read. Let me make this just a little bit bigger. Okay. So we're talking about the hydrogen atom. So the electron and proton of a hydrogen atom are separated on the average by a distance of approximately 5.3 times 10 to the negative 11 meters. What I want you to calculate is the magnitude of the electric force and the gravitational force between these two particles. So just to remind you what we just said earlier, the electric force is given by the constant k times q1 times q2, and then you divide by the distance between them squared. The gravitational force looks pretty similar to this. It has the mass of one times the mass of the other one, and then you divide by the distance between them squared as well. So that you have the 1 over r squared dependence. We call both of these inverse square laws. Okay. And just to remind you what the values of the constants are, the constant k is equal to about 9 times 10 to the 9. And the constant g, big G, is about 6.67 times 10 to the negative 11. So what we have here is basically an electron and a proton that are separated by a distance r that's equal to, right here, 5.3 times 10 to the negative 11. And so, meters. What I want you to calculate is the value of the electric force between the two particles, the value of the gravitational force between the two particles, and then finally what I want you to do is to calculate the ratio of these two. And what we'll do is we'll do the electric force divided by the gravitational force. Okay, I'm going to give you 5 minutes. It's 3:19, so we'll check back here in 5 minutes. Anyone have any questions about the setup? All of the data up here is for this problem too. So you've got mass of the electron is there, mass of the proton is there, and then their charges. Okay, so give it a shot. When you get an answer, you can type it into the chat. 2 more minutes. Anyone else get an answer for any of them? Feel free to put it in the chat if you do. I think all 3 of those are right, Delvin, yeah. I think Cam's is wrong. But those numbers are what I got. I'll give you 1 more minute. Make sure you can get all the right numbers. Yeah, if you get the same ratio, then you're good. Okay, that's about 5 minutes. Let's go through the answers to these things. So, Fe, I'm just going to write quickly down what the equation would be. You do K, so 9 times 10 to the 9. You're going to want to get pretty good at using scientific notation with your calculator. There's a way to write this in your calculator where you just write it as this, right? I'm going to write, I'll write what your calculator would look like over here on the left. So you'd put that, depends on what kind of calculator you're using, right? But almost all calculators have some feature where you can write 9 times 10 to the 9 as 9e9. And we're multiplying that times the charges of the particles for the electric force. So the charge of each particle is about 1.6 times 10 to the negative 19 coulombs. We don't really care so much about all these other digits. You can use more digits if you want, but you're still going to get pretty much the same answer. They both have the same charge, so we're going to square that. And then we just divide by our distance squared. So 5.3 times 10 to the negative 11 meters. And then that's squared. Okay. What this would look like if you put it in your calculator is 9e9 times 1.6 e negative 19, and then you'd be dividing by 5.3 e negative 11, and then these are squared, so this would be squared and this would be squared. Okay, and if you plug all that in and you see what you get, what you're going to get is about something like 8.22 times 10 to the negative 8. And the unit, of course, is newtons. Okay, or written in scientific notation, 8.22. Well, these are both scientific notation, right? But negative 8 newtons. Okay. We'll go through gravity. I'm not going to write all the answers in for gravity. We'll just say you plug all the same numbers in, except the masses are what you're plugging in now. So you need this mass and this mass. I'll write it out. Why not? So it's going to be 6.67 times 10 to the negative 11. This is the big thing that's different between the two of them for sure. Newton meters squared, this time over kilograms squared, multiplied by their masses, so 9.11 times 10 to the negative 31 kilograms times 1.67 times 10 to the negative 27 kilograms for the proton, divide by the same distance squared, 10 to the negative 11 meters, square it. This one will give you an answer of, I should have done a different color for that one. I could just make it a different color so it stands out a little bit more. I'll just make that black. The answer you'll get for this one is 3.6 times 10 to the negative 47. Is that the same thing as one? Let's see. Yeah. 3.6 times 10 to the negative 47. That's also Newton. So you can see that the gravitational force is obviously extremely weak. Now, there's a lot of reasons for this. One is because the masses are much, much smaller than the charges, just from a numerical perspective. But the other thing is that you're multiplying by 10 to the negative 11 in this case, whereas with the electric force, you multiply by 10 to the 9. So almost like a trillionth compared to 10 billion, right? This overall constant that shows up in the front here is really a description of exactly how much stronger the electric force is than the gravitational force. And the biggest kind of impactful thing to say is if you take the ratio of these two, as you calculated there, you take the electric over the gravitational, you get something that's on the order of about 10 to the 39 with no units, right? Now, this doesn't mean that the electric force is always 10 to the 39 times as great as the gravitational force. It just means that that's the case here. However, it's generally the case that in almost any situation you're going to have a stronger electric force than you're going to have a gravitational force, unless you're talking about like massive objects like suns and planets and stuff like that are neutral objects. The electric force is really, really strong, right? And something that I didn't mention before is that when you touch something and you ask yourself, what am I feeling? Let's say you pick up an object like a cup or something like that. When you get this where you guys actually see that. When you touch something and your fingers can't actually push through the object, you might say it's because of the structural integrity of the cup or something like that, right? But really what's happening on the most fundamental level is when you touch an object, there are electrons in your finger and there's electrons in the cup, and they're repelled from each other, and the closer you get, the bigger that force becomes. Almost all forces that you feel on an everyday basis are electrical. Anytime you touch something, anytime you taste something, or smell something, or hear something, well, hearing is that's kind of it's still really electrical forces at the end of the day, I guess. The electrical force dominates all of your experiences, right? Gravity is just the force that draws you to the earth, right? But if you think about it, when you're standing, right? You think about, here, let's draw a little picture here so I can describe instead of... When you're standing on the surface of the earth, right? So let's say this is the surface of the earth and I'm drawing it intentionally curved. Right? In physics 1A, you'd say, okay, well, there's a normal force right here, right? And there's a normal force right here. And those are basically counterbalanced by your weight, which acts kind of, let's say, from your center of mass down this way. Your weight. And pretty much what you would say is that these two normal forces add up together to be equal to your weight, right? But what is the normal force? Well, the normal force is created by electricity. And let's just look at just your shoe for a second, okay? So your shoe, let's say this is a person's foot, right? Down here there's a bunch of little electrons, and inside of here there's a bunch of little electrons. They're all negative, and they just can't push through each other. It's that simple. So these are electrical forces that are repelling here. And I want you to think about the following kind of scale of this thing. Think about the size of your foot, okay? Everyone's got different feet sizes, right? But let's say your foot is about a foot long and like maybe 2 inches wide, maybe 3 inches wide, I don't know. Not big, right? Your foot's really tiny, right? So your foot can't pass through the earth, right? But in order to keep your foot actually firmly supplanted on the earth itself, you need the mass of the entire planet to keep you there, right? Gravity is so weak that you need a planet, something the size of a planet like the earth, to hold your foot on the ground, but you only need a few electrons, well, let's say a few trillion electrons in your feet to prevent yourself from falling through the earth, whereas you need the whole earth itself. Several moles of molecules, right, for gravity to work, right? Gravity's weak, electricity's strong. That's pretty much what we're trying to say here. Okay, any questions? All right, let's talk about superposition of forces. This is not 2 words, it's 1 word, superposition. What is that? What is that it's doing? Okay. Superposition of forces. Okay, so this is something you may or may not have learned in Physics 1A. Regardless, it's always a good idea to repeat it. So suppose we have a situation where I have a positively charged particle right here, and I call that particle Q1, okay? And let's say within the region, I have another positively charged particle over here, and we'll call that one Q2. And let's say that this one is fixed in place somehow. And over here, let's say that we have, let's just only use positive charge. I think that makes it simpler. We have another positive charge over here, Q3. Okay. And just for the sake of putting some numbers to this, let's say that Q2 is 2 coulombs. Let's say that Q3 is 3 coulombs. And let's say that Q1 is 1 coulomb, just so we have some numbers to play with, okay? So we know that Q2 is going to place a force on Q1, and what direction would it go? Now, we're saying both of these are fixed in place. These are not moving. This is the only one that's allowed to move, okay? The one on the bottom here, Q1, is allowed to move, all right? The other two are fixed in place. Now, if I was to just look at Q2 and Q1, can you tell me what direction, roughly, would the force on Q1 be? Would it be up towards it or down and away from it?
Away.
Yeah. And we could represent that with a vector, right? Let's just actually use a vector here and say that the force of this one on this one is going to go along a line between their centers, and it's going to kind of point off like that, right? And I'll make it, let's say, that long, okay? I'm going to call that the force of object 2 on object 1. And we know it's a vector, right? We can do the same thing for Q3. We would say, okay, well, there's a force of Q3 on Q1. The force that Q1 experiences due to Q3, what direction does it point? The force of 3 on 1, what direction would that point?
Down and to the left.
Down to the left, that's right. So let's draw a little vector in here. Now, is it going to be bigger or is it going to be smaller than the force from Q2? Should I make it the same length? Okay, they have to be in line with each other, right? So we'll go like that. Just kind of try to draw in line. Should I make it shorter or should I make it longer?
Longer.
Longer? And why is that? Because this charge is bigger, right? Okay, so we'll make this one slightly longer. It's probably too long. It's a 2-to-3 ratio, something like that. So we call that one the force of 3 on 1, right? Then the question becomes, what's the net force acting on Q1? And the answer is it's simple. When we say superposition of the forces, really what we're doing is saying add up forces, right? If I want to know what the net force acting on an object is, which we usually represent by some symbol like a sum over all forces, all I have to do is just sum up all the forces acting on it. So if I take force F31 plus force F21, then that's going to give me what we call the net force acting on this object. Now, in order to do that in this case, we can use something that we learned from Physics 1a, where if I just take this vector, right, and I place it tip to tail with the other vector, that allows me to add the two forces together, right? And does anyone remember how you do that? How do I add, if I have a vector this way and I have a vector this way and I want to add them, what do I do? I'm sure you guys know how to do this, right? How do I add this vector plus this vector?
From Q1 to the tip of
Exactly.
F31.
Exactly. So we basically just take another vector and we connect the tail of this vector. Whoops. Control Z. Uh-oh. It's going to start doing weird things for me now. I think that's okay. Like that. And that's going to be basically the net force. Right? We just get it by vector sum, right? And that's what this says. When I have multiple forces that act on a particle, I add up all the individual forces. If I had 5 forces acting on a particle, I would add up the 5 forces. Okay? So the net force acting on Q1 is going to be down and to the left this way. And that makes sense because this one's bigger, but they're both positive. So we know it's going to go down. It ends up going left because Q3 is a little bit bigger than Q2, right? Now that's the force at that point in time. Because if you let the system evolve and the object starts to move and accelerate, right, it's going to change what the force is, right? Because you're going to get farther away from these objects. So I'm only talking about the force at this moment in time before the particle starts to move. This force is not a constant force at all. It's a force that would change relative to the position of the particle over time, right? Okay, so let's look at 3 examples of problems where we do superposition of forces, okay? We're going to look at a particle, we'll look at 3 particles in a line, then we'll look at 3 particles in a plane, and then we'll look at another set of 3 particles in a plane, basically. But this will be the first one that we're going to do right here. And again, I'll probably just let you all solve this one yourselves and then come back. And I know that one of your homework problems is like this. You might as well take some time to think about it. Now, can everyone read the problem if it's at this size, or do I need to make it a little bit bigger for anyone that's on a smaller screen? Do you want me to make it bigger, or is it okay?
It's okay.
Okay, so someone said bigger. I'll make it a little bigger. Is that okay? Okay.
Yeah, that's fine, Professor.
Okay, so this is the scenario. Let's read it. The question is, where is the net force 0? Now, by the way, I took all of the example problems from a different textbook. I like to use, let me see if I can show you it. This textbook here, Physics for Science, Physics for Scientists and Engineers with Modern Physics. So if you're interested in figuring out where these examples came from, they come from this book right here. This is what the cover looks like. This is the 8th edition that I'm drawing from. I really like this textbook. I think that their diagrams are really nice. The diagrams in the university physics book, when you try to transfer them over to to OneNote, they just don't look very good. But these diagrams look really nice. And there's a lot of like geometric beauty in the Physics with Scientists and Engineers book. So it's by Surway and Jewett. If you want to go pick it up yourself, you can. Oops. That's what it is right there. That's the authors. So it's a really good book. I like their explanations. They're not always better, but sometimes they're better. So anyway, here's our problem. Where's the net force 0? So 3-point charges lie along the x-axis as shown in the figure here. So we've got a positive charge called Q2, a negative charge called Q3, and a positive charge called Q1. I think that Q1 and Q2 are fixed, but Q3 is free to move. And we can put it wherever we want to. Now our goal is to put it at a location where the force that's experienced is going to be 0. Okay? Positive charge is 15 microcoulombs. It's at x equal to 2 meters here. You can see that here. There's the xy axis. The positive charge Q2 is 6 microcoulombs. It's at the origin. And the net force acting on Q3 is 0. What is the x-coordinate of Q3? So our goal is to basically figure out, as is very common in mathematical problems, what is x? So should I set this up anymore, or should I let you all just... do you feel like you could just jump right in? Or should I set it up? What do y'all think?
Can you set it up for like the first problem? So because you said there's another one similar to this one in homework, so at least give us some kind of visual.
Well, okay, I'll just say it this way. So if I put a negatively charged particle in between the two positive charges, right? We know that it's both going to be attracted to the left one and it's going to be attracted to the right one, right? Everyone agrees with that. We also know that the force that it feels, in general, is going to be given by K times, let's call it Qi times Qj, divided by, because we have a Q1 and Q2 and Q3 here, I don't want to, divided by the distance between them squared, right? So we have a general expression, but we're trying to find a place where the force is 0 on this particle, right? What would have to be true about F23 and F13? That is to say, the force of 2 on 3 and 1 on 3. What would be true about these two forces?
Same magnitude.
Yeah, same, right? So we basically say that F23, the magnitude, has to be the same as F13, the magnitude. So it'd be something like KQ, that's weird. We got ink to shape on, so it's going to do weird things. KQ1, sorry, not Q1. Oops. So Q23 would be Q2 times Q3. We divide by the distance between them squared. Now, on our picture, what's the distance between 2 and 3? On this diagram.
2 meters.
What is it?
2 meters.
Nope, that's the distance between 1 and 2. We want the distance between 2 and 3.
Oh, 2 minus x.
Nope.
Oh,
Also
x,
wrong.
x.
Just x.
The x.
Okay, and then this needs to be equal to k times... The other two are Q1 and Q3. And what's the distance between those two? From here to here is that distance. And there we go. Now you just need to solve it. I'll give you about 5 minutes. See if you can solve for x. And if you need more time at that point, I will let you have more time. A lot of things cancel out, right? The K's cancel, the Q3's cancel. So, and of course they didn't give us the value of Q3, so it kind of has to cancel. But you'll be left with one unknown, which is x, and you can solve for it. So give it a shot. You got one more minute, and I'll see how everyone's doing. If you do get an answer, you're more than welcome to type it in the chat. All right, so a couple people got some answers. Seeing as they're all pretty close to each other, that's probably right. I think Delvino's answer is exactly right. Maybe I'm wrong. Okay, that's 5 minutes, and since several people have already solved it, if you weren't able to solve it in that time, that's okay. The whole point is just giving some time to actually think about it is really the idea here. Let's just briefly rush through the solutions. So, like I said at the beginning, a lot of things cancel. And what I'm going to do is just multiply the x squared over. Let's see, Q2 was equal to 6 microcoulomb, so we could write 6 microcoulomb. And multiply that by the denominator here, which is 2 meters. And that should be equal to Q1, which is 15 microcoulombs. And we multiply that by x squared. Luckily, all the units cancel out now too, so this unit's gone and this unit's gone. We don't have to worry about the micro part. We just need to expand this out. So, yeah, I guess we'll just say 6 times, let's see, 2 meters squared would be 4 meters squared. Minus 2 times this, we'll get 4 meters times x, and then plus x squared. Should all be equal to 15x squared. You could do this any way you want to. I guess we'll just multiply it out. Seems reasonable. Did I do that right? 2 times 2 is 4. Negative 2 times 2 is 4x, and then xx squared. Yeah, it looks right. So we'll get 24 meters squared. And then we'll just do one more step here. So 6 times x gives us 6x squared. We need to subtract 15. 6 minus 15 would be negative 9. Is that right? I think so.
Yes.
Yeah, we just need to put that in a quadratic formula, right? Which means probably want to change the order. Maybe divide by 3. So if we divide by 3, that'll become an 8. Divide this by 3. We'll divide everything by negative 3. That's what we'll do. So we'll put, this will become positive 3x squared. If I divide that by that one by negative 3, then I'll get positive 8. And if I divide that by negative 3, I'll get negative 8. Okay. And that equals 0. Is this something you can factor? Probably not, since you guys got a weird number, right? So I'm just going to go ahead and say that from here you can use this to use the quadratic formula, and you should get something like 0.775. What was the other answer you all got, by the way? What was the negative answer you got? You should have gotten a negative answer too. Did you? It doesn't have to be a negative answer. It's either going to be a negative answer or a number greater than 2. One of those are the two options. Negative 3.44. Is that what other people got too? Yeah, cool, great. So we're definitely going to take the number that lies between Q1 and Q2 here. Now, let's just think about this. The answer we got ended up being closer to Q2. Is that reasonable? Why is the answer not right in the middle? Why is it closer to Q2 than it is to Q1? What's the reason for that? Why is the number that we got less than 1, less than the point in the middle? Any ideas? Which charge is bigger? It's Q1, right? This is 15 and this is 6, right? So if I want to find a place where the two forces balance each other, if the charges were equal to each other, it would definitely be right in the middle, right? But because the 6 is smaller, right, we need to be closer to the 6, right? To get the same force from both of them. Okay. So you all have a homework problem. I believe it's almost exactly like this. So hopefully should be able to do it. Okay, so that concludes our discussion of forces. And the next thing we're going to discuss is fields. But just to break things up here, let's go ahead and let's actually look at some demonstration of static electricity. So here's a video of static electricity things. You should be able to hear this. Oh, I don't know. Let's just see. Tell me if you hear this or not.
No.
I don't even
No,
hear
not
it.
at all.
Wait, is it making sound at all?
I think I had to stream the video.
Yeah, I know. I was wondering if by using... Why am I not hearing the sounds? That's one question. Okay, so we'll do
That's
that.
really weird.
So you're gonna have to rejoin the stream. Will you? Let's see what happens. I can just change windows. And I do this window here. Go live. Let's see if you can hear it now.
Yep, very bass heavy.
I can't hear it at all. You guys can hear it?
Yeah, we can hear it.
Yeah.
Okay, so go ahead and enjoy. Do I need to turn it down? By the way, you can do almost all of these at your house. I don't know if you saw what they did at the beginning. Let's just start this over again so you can see what they did. It's so weird that I can't hear it. You guys can't. Oh, I bet it's playing through my speakers. So the last one's pretty simple, right? Styrofoam plates, piece of cloth, rub them. You should be able to do that at home very easily. I don't know if you all have PVC pipes, but you might have something that's plastic. Anything that's plastic will substitute for PVC pipes here. Okay, so this is one you can definitely do at home too. You can do it with a plastic comb too. You can just take. You don't have to have a cup, but you can just take your like water from your faucet and just make sure it's going really slowly. Then rub a comb on your shirt or something or your hair, and bring it really close, and it'll bend the water just like that. So I want to go back to one of these. This one. And see if you all can't tell me what's happening here. So you notice that she rubs the rod, which we've said before means that the rod is going to become negatively charged, right? So what is it that's causing these two pieces of metal to deflect away from each other? And she brings it close. You know,
Is
what
it
I guess?
because
Go ahead.
all the positive is going out?
What do you mean?
The positive charge
Going up to what?
to the tip of the wire.
Yeah, that's pretty close to right. What does that mean about the two leaves at the bottom? If a bunch of positive charges were going to the top, what does that mean about what's happening to the leaves at the bottom?
They become negatively charged, so they repel.
Yeah, that's exactly right. So it's not really positive charges that are moving though, right? It's actually electrons, right? So there's electrons in the piece of metal here. You bring the negatively charged object, the negatively charged electrons run away. They go as far away as they can, which they can't really escape into the air because the air is an insulator. So they get trapped down here on these leaves, and then the leaves repel each other, exactly as you all